Hello everyone, my name is Mikel and today I'm going to present part of my master thesis in healthcare technologies, and this project was developed with the help of the Robotics and Vision in Medicine lab from the King's College London. So in robotic surgery we have some good things about it, that it increases the precision of the task we can perform. And this helped the surgeons to perform more complex tasks that we usually couldn't make in bare hand. And for example, a surgery, or it could help us access points that we couldn't probably access safely in other type of situations. But on the other hand, we have, as we are not into the real system, so we are looking into a console and working with some kind of joysticks or so we are losing this type of force feedback that we are having when we are working with bare hands. And this makes for the surgeon to lose this lack of perception into force, but as you are seeing images in a 2D screen, you are losing this lack of depth perception that you are having from the real world. So to solve these two tasks, there are many approaches. One of them is to use a haptic interface to provide the user force feedback. And for the perception of positioning and of this third dimension, we have active constraint that help the user with the navigation. And one of the most common one is to just help the surgeon navigate around a given path, or you can avoid its movement over a forbidden region and just push out of it. So our idea here in the project was to find a simple way of creating active constraints in SOFA and use a haptic interface to provide this force feedback of just attaching to the line or just pushing out of some certain points to the user. So as the COVID-19 pandemic, we have like some problems, as probably all of you. So I had to do it away from the university, the project. So we decided to buy the most inexpensive device, a haptic device. So it's the Falcon haptic device. It's only 30 degrees of freedom. It has 3 arms connected to motors. And to connect this, we used the Sofa Happy plugin. And it was a real mess to connect. It was like the hardest part. But I mean, it was a nice work. And once we have the haptic device connected into the interface, what we make was to create a Sofa Python script, and we created a sliding constraint between the haptic device model, modeled as a sphere, and we create a mesh over an organ. So we just cover the organ with a point mesh in this case. And we selected some predefined points, and we wanted the haptic device only move over these points. So we just generate a single sliding constraint that will update when you are getting close to every point. So if you're moving forward, it will update to the point you are closest to the one and the next one. And if you're moving backwards, it will automatically update from the point you are closest one and the previous one. So you will just move only over the line. And if you try to move away from the line, the haptic device will automatically pushes you back to the path. So you will feel this force feedback. And I will have here a video showing how the active constraints work. So more or less, if you see, I try to move. So you will see some interactions there. And you will see how the ball will move back and forth. And when I try to move outside, the line will interact with the ball and it will just make it go back. And if you can see, that will be more or less the... Oh, shit. Okay. Yeah. So that's the idea of this algorithm. And then we wanted mainly to be effective, and we demonstrated to be effective. So if we don't use constraint, we try to move the haptic device over the lever with including the formations of the lever, we'll have a mean deviation of 5 millimeters. And when applying this constraint, we only have like 0.009 millimeters of deviation from the predefined path over the 15 points we have already preselected. And as I previously mentioned here, without constraints, as we are approaching to the last part of the lever, in which we are moving in the set directions in this depth, as we don't have this perception of how much we are moving into the screen, like inside the screen, we are losing again the effectiveness. And here you can see that you are not losing the effectiveness even if you are moving in this third dimension of the image. And then to see that this is like why we choose 15 points and not other things. So as a sliding constraint is mapped as a line, as a straight line. So we saw that if we take this straight line and make like the straight line too big, you will move away at some points of the path you want to follow. So you can see how at 50 points you have like the less error possible. So that's why we selected to go from the shortest distance possible and not when using the sliding constraint already present in the SOFA library. And the next one was to try it with not only a straight line, but doing some fancy things. For example, some things that probably are very hard to do with bare hands. I mean, people with like expertise could do the circular path or this set path probably with like a very good precision. But as I can demonstrate, I'm like really bad following things, and I couldn't do it like very, very precisely with this algorithm. And for example, for the circular path, we'll have a bit more of deviation from the control points we have selected, but still we have like very, very little deviation compared to the 5 millimeters we have with bare hand in a straight line path. And for example, I will just show you, for example, how the circular path looks like. So yeah, when you try to move outside the circle, it will just direct you back to it, and you could move freely. And you have a distance. You will have a distance to the lever to not interact continuously with it. So you could probably safely navigate around any organ probably. And the idea of this, we demonstrated that using this approach for active constraints to show that are effective in some simulated scenarios for safe navigation. And but the next steps, as this has been like 3 months, 4 months work, the next steps will be to try to find more complex curves to express this active constraint instead of using only straight lines, because straight lines for some of the modeling we have to do, or some of the type of deformation we are considering here, it will lead us to have more errors. So probably splines or polynomial curves will be a better approach to express these active constraints. And the next step will be to test these constraints on a real system. For example, a concentric tube robots, but as the ones presented in the first section of robotics will be a good trial for this algorithm. So thank you very much.
Thank you very much, Mikel, for the presentation. Nice. It's your master work then, right? Mm-hmm. Is that correct? Yeah. Very nice work. You've got already a question from Paul. Paul is asking, so very interesting presentation. My question is, which data field are you using to toggle whether the constraint is active or inactive? Are you doing that from within the Python controller?
So I was just taking the position of all the points of the lever at every animation step. So I was checking if the lever was deforming or not. And what I try is mapping the 15 control points to how the lever was deforming. So I just compute the difference. So using SOFA, I just make a bigger lever mesh that map to the smaller lever, so it will deform with the smaller lever when interacting with the haptic device. So in the Python animation, I just check if the lever points were changing or not. That was more or less. I was just updating the position of the points every iteration of the animation. So I don't think if that's your more or less answers your question.
He will tell you. I think Paul will tell you.
Yeah.
And there is a second Paul preparing the question, Paul Baktik from Mimesis. So yeah, it's answered. Perfect. And we'll still have time for question. Paul, no question anymore, finally? Okay. Is there any other questions? So apart from Paul, the polls, is there any other question for Mikel?
Maybe I can ask them.
Perfect.
Okay.
Yeah, what is with the voice? Perfect.
Yes.
Go ahead, Paul.
So the experiment you showed that you made with your interface were interesting, but what you tried was only with simulated organ, with the position that you were very sure where the lever was. And so my question is, when you will maybe in a future work try to test it on a real system, you will need to perform some registration of the organ. And this registration can be wrong. How do you plan to let the user maybe, because here you are constraining him very hardly on the surface.
Yeah.
But when you don't really know what the surface is, maybe do you have any idea to how to let the user be more free?
So most of the approaches regarding active constraints do add a lambda parameters to just to just measure how much constraint you are at each point. So it will be something similar to that, in which you just put lambda 1 if you want to be as constrained as possible, and just having it back to 0 to have free movement. So if you are not certain, you can probably just play with that lambda parameter. From the other, in the real systems, so now we are in the lab, they are working with a I model, and we are planning to apply the active constraints to the new I model, so to see if it works with more complex organs in this case.
We can't hear you, Hugo.
Thank you, Guillaume. Yeah, so I was thinking, yeah, Paul, just thank you. Nice presentation again, Mikel. If there is one last question for Mikel, and then we'll move to the second presentation of this session. So I had just a curiosity. What is actually and do not hesitate to post the question in the meantime, or keep your questions for the next break to get a private chat directly with Mikel. Mikel, what is actually the robotic system that you are targeting afterwards? Do you have already that at KCL, or is that not defined yet for the robots that you're?
So there is one of my supervisors from the master thesis is working in a robot model, in a concentric tube robot model. So the first plan is trying to take this model to SOFA in a way. So we are seeing how to do that. So that will be the next step. Great.
Thank you. I check. Yeah, for the moment, no additional questions. So thank you again, Mikel. We're right in time, so it's perfect. We're gonna move on, and again, there will be time. Thank you. There will be time for at the break for asking further questions to Mikel.